We can see the universe's very first light. This ancient glow, called the cosmic microwave background, is a fossilized echo from the dawn of time, and it holds the secret recipe for our entire cosmos. By the end of this journey, you will understand how a faint cosmic whisper revealed the universe's complete history, its composition, and its ultimate fate. We will uncover why this light was an accidental discovery, how its tiny ripples built every galaxy, and what mysterious cold spots might hint at realities beyond our own. What do you think it means that we can observe the infinite universe from our small planet? This ancient light is the afterglow of creation itself, known as the cosmic microwave background. It is the leftover heat and the very first light that could travel freely through the cosmos. Its story begins when the universe was an incredibly hot, dense soup of particles and energy, a searing fog where light was constantly trapped, bouncing from one particle to another. For nearly 13.8 billion years, the universe has been expanding and cooling, and this primordial radiation has stretched along with it. The original brilliant flash of optical light has been cooled and stretched by the expanding fabric of space into the faint microwave glow we can detect today. Think of it as a cosmic baby picture, a snapshot of the universe at the tender age of just 380,000 years. This was the pivotal moment when the universe cooled enough for atoms to form, allowing light to finally break free from the plasma and travel across the cosmos. That first flash has been traveling for almost the entire history of existence, carrying with it an imprint of the infinite universe for anyone who knows how to look. What secrets are written into this fossilized echo from the dawn of time? This faint whisper from the beginning of time was not a complete surprise. Decades before two radio astronomers would stumble upon it, the universe's oldest light had already been predicted on paper. In the 1940s, a team of brilliant theorists, George Gamow, Ralph Alpher, and Robert Herman, were piecing together the story of the Big Bang. They were working on a monumental puzzle, figuring out how the very first elements in the cosmos were forged. Their calculations showed that in the first few minutes of the universe, the extreme heat and density would have cooked simple hydrogen into helium, a process we now call Big Bang nucleosynthesis. But their work led them to a stunning and unavoidable conclusion. If the universe truly began in a hot, dense state, then it must have been filled with a brilliant, searing light. And as that universe expanded over billions of years, that initial flash would have cooled down and stretched out. They calculated that this relic radiation, the faded echo of creation, should still be all around us, permeating all of space as a uniform, cold glow. They predicted a temperature only a few degrees above absolute zero. Think of a blacksmith pulling a white-hot piece of iron from the forge. At first it glows brilliantly, but as it cools, the light it gives off shifts in color from white to orange to a deep, dull red. The universe has been cooling for almost 14 billion years, and Gamow, Alpher, and Herman essentially predicted the color of that cooled-off cosmic metal. They had, in theory, discovered the cosmic microwave background nearly 20 years before anyone would point a telescope at it. Why do you think such a profound prediction was largely overlooked for so long? That profound prediction was waiting for its moment of discovery, a moment that would arrive not through a grand, targeted search, but through sheer accident. At Bell Labs in New Jersey, two radio astronomers, Arno Penzias and Robert Wilson, were trying to use a giant, ultra-sensitive horn antenna for cutting-edge communications research. But their work was plagued by a maddening, persistent problem. Their instrument picked up a constant, low-level static noise that came from every direction in the sky, day and night, and they could not get rid of it. They were meticulous. They checked every possible source of interference. They pointed the antenna at New York City, thinking it might be urban radio chatter. They even suspected the equipment itself, and famously, they blamed a pair of pigeons that had nested inside the giant horn. They carefully evicted the birds and scrubbed away what they described as a white dielectric material, which is a polite term for pigeon droppings. But the hiss remained. It was an inescapable, universal whisper that they could not explain. They had no idea they were listening to the oldest sound in the universe. Meanwhile, just a short distance away at Princeton University, a team led by physicist Robert Dicke was actively building a detector to find this very signal, the cooled remnant of the Big Bang that Gamow and his colleagues had predicted. When Penzias and Wilson, frustrated, made a phone call to Princeton describing their mysterious noise, the pieces of the puzzle clicked into place. The Princeton team immediately understood what the Bell Labs scientists had found. That annoying, inescapable static was the cosmic microwave background. It was the faint, cooled echo of the universe's birth, bathing the entire cosmos. For their accidental discovery, a finding that confirmed the Big Bang theory and transformed our understanding of the cosmos, Arno Penzias and Robert Wilson were awarded the Nobel Prize in Physics. It is a powerful reminder that sometimes the universe's greatest secrets reveal themselves not when we are looking for them, but when we are simply listening carefully enough to hear a persistent signal we do not understand. That faint cosmic hiss Penzias and Wilson discovered was not just ancient, it was unnervingly smooth. No matter where they pointed their antenna across the sky, this afterglow of the Big Bang registered the exact same temperature, a frigid 2.725 degrees above absolute zero. This incredible uniformity was a profound cosmic clue. It meant the early universe was in a state of near-perfect thermal equilibrium, a hot soup so well mixed that every part was virtually identical. But this created a monumental puzzle for scientists. How could regions of the universe that are now on opposite sides of the sky, billions of light years apart, possibly have the same temperature? According to the standard Big Bang model, these regions would never have had time to exchange heat or information. It was as if you walked into a vast, crowded room where thousands of people you had never met were all holding a cup of coffee at the exact same temperature. They had no way to communicate and coordinate this, yet they all did. This cosmic smoothness seemed impossible. The universe, it appeared, had to have been much, much smaller at its birth, small enough for every part to be in touch with every other part, achieving that perfect equilibrium. But then how did it get so enormous so quickly? The solution to this puzzle led to one of the most breathtaking ideas in all of science, a concept called cosmic inflation. This theory proposes that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential, faster-than-light expansion. In an almost unimaginably brief instant, a subatomic speck of space was stretched to a size larger than our entire observable universe today. This violent growth spurt smoothed everything out, ironing any wrinkles and equalizing the temperature across the entire cosmos before it had a chance to become lumpy. Inflation solved the smoothness problem, but it also planted the seeds for everything to come. What could possibly cause the fabric of reality itself to stretch so violently in a single, transformative moment? Yet that perfect smoothness was a cosmic deception, for the infant universe was not truly uniform. Woven into the fabric of that primordial light are incredibly faint ripples, tiny variations in temperature no larger than 1 part in 100,000. To grasp the staggering subtlety of these fluctuations, imagine a perfectly smooth ocean that stretches to infinity in every direction. Now picture a series of gentle swells on that ocean, but these swells are so minuscule that their height is no greater than the thickness of a single sheet of paper laid across its entire vast surface. These are the anisotropies, the faintest of cosmic whispers imprinted on the CMB. They are the most important features we have ever mapped, for these tiny ripples in temperature were, in fact, ripples in density. Slightly warmer spots were regions where the primordial soup was just a little bit denser, packed with a little more matter and energy. Slightly cooler spots were the corresponding shallow voids. And in that subtle difference lies the origin of everything we see. Gravity is an irresistible force that amplifies small differences over time. Over hundreds of millions of years, gravity began to pull relentlessly on those slightly denser patches. The extra tug drew in more and more gas, piling it up, creating the first clumps of matter in a sea of darkness. These clumps grew, merging and colliding, eventually forming the vast cosmic web of gas clouds, stars, and galaxies that fill our night sky. Every galaxy, every star, every planet, and by extension, every one of us owes our existence to the gravitational blueprint written into those tiny temperature variations. We are the grand evolved consequence of a whisper in the first light. To read the blueprint of the cosmos, we needed a map. This monumental task fell to a pioneering satellite named the Cosmic Background Explorer, or COBE. Launched by NASA in 1989, its mission was audacious: to scan the entire sky and measure the faint whisper of the cosmic microwave background with a precision never before imagined. For years, the data trickled in and the scientific world held its breath. When the COBE team finally presented their first full sky map of the infant universe in 1992, it was a moment of pure revelation. The image showed the predicted, near-perfect smoothness, a universe bathed in a uniform glow, but superimposed on that background were the faintest of mottled patterns, tiny splotches of warmer and cooler temperature. These were the primordial ripples, the density variations that theory demanded must exist. COBE had not only confirmed the black-body spectrum of the Big Bang's afterglow, it had captured the very seeds of cosmic structure. The lead scientist for the team, George Smoot, famously described the sight as like looking at the face of God, for proving the existence of these critical fluctuations and cementing our understanding of the universe's origins. The COBE project's leaders were awarded the Nobel Prize in Physics in 2006. This was not just a map, it was our first clear photograph of the cosmic infant, and it showed the wrinkles that would one day grow into a universe of galaxies. COBE grainy baby picture was just the beginning. The next great leap in our cosmic vision arrived with a mission called the Wilkinson Microwave Anisotropy Probe, or WMAP. Where COBE had revealed the faintest whispers of structure, WMAP was designed to listen with astonishing clarity, transforming those whispers into a detailed cosmic biography. Launched in 2001, this satellite spent 9 years staring into the depths of space, gathering data so precise it would redefine our place in the cosmos. The map it produced was not just an image, it was a celestial cartographer's dream, a high-definition portrait of the infant universe where every subtle swirl and temperature variation was captured with razor-sharp precision. This was no longer a blurry snapshot, it was a finely etched blueprint. From this exquisite data, scientists could measure the fundamental characteristics of our universe with a confidence never before possible. They pinned down the universe's age with remarkable accuracy, calculating it to be 13.77 billion years old. They precisely measured the composition of the cosmos, confirming that the familiar atoms making up stars, planets, and us account for less than 5% of the total universe. The rest, they confirmed, is the mysterious dark matter and the even more enigmatic dark energy. WMAP also answered a profound question about the shape of space itself. Is the universe curved in on itself like a sphere or warped outward like a saddle, or is it flat? The data from the patterns in the ancient light gave a definitive answer. The geometry of our universe is flat, meaning that parallel lines will never meet, and the rules of Euclidean geometry we learned in school hold true on the grandest of scales. Think of WMAP as the ultimate cosmic surveyor, using the oldest light in existence to measure the size, contents, and very shape of our cosmic home. What other profound truths are still hidden within the subtle patterns of this primordial glow? While WMAP gave us a clear blueprint, the Planck satellite delivered a pin-sharp masterpiece. Launched by the European Space Agency in 2009, this observatory was a technological marvel of sensitivity, designed to listen to the universe's first light with an ear so fine it could hear the faintest cosmic nuances. Its mission was to observe the cosmic microwave background with a resolution and precision that dwarfed all previous efforts, and the map it produced was nothing short of breathtaking. Imagine looking at a photograph that was once grainy and out of focus, and suddenly seeing it rendered in hyper-realistic detail, where every single pixel holds a universe of information. Planck's portrait of the infant cosmos was so exquisitely detailed that scientists could study the tiny temperature fluctuations not just as blobs, but as complex patterns with specific sizes and distributions. This incredible clarity allowed cosmologists to refine our cosmic measurements to an almost unbelievable degree, like a master clockmaker adjusting the gears of reality itself. Planck confirmed the universe's age with even greater certainty, placing it at 13.8 billion years old. It gave us the most precise recipe for the cosmos yet, measuring the exact proportions of ordinary matter, and dark energy. But its most profound impact was testing the very foundations of our understanding, pushing the limits of theories like cosmic inflation. The data was so precise that it revealed subtle anomalies, tiny features in the ancient light that our current models struggle to fully explain. Planck did not just give us a better map, it gave us a deeper, more complex, and in some ways more mysterious picture of our origins. What do these subtle imperfections in the earliest snapshot of reality tell us about the true nature of the cosmos? This cosmic recipe, decoded from the ancient light, reveals a universe far stranger than we ever imagined. The data from Planck and WMAP gave us the ultimate ingredient list for everything that exists. The stars, the planets, the very air we breathe, all the ordinary matter made of atoms, accounts for a mere 5% of the cosmos. It is the cosmic equivalent of the foam on a vast, dark ocean. The next ingredient is dark matter, an invisible and mysterious substance that makes up about 27% of the universe. We cannot see it or touch it because it does not emit, absorb, or reflect any light. Its presence is only felt through its immense gravitational pull, a ghostly grip that holds entire galaxies together and sculpts the large-scale structure of the cosmos. Without this dark matter scaffolding, galaxies would simply fly apart, but the most dominant and most baffling component is dark energy. This enigmatic force makes up a staggering 68% of the universe. Unlike gravity, which pulls things together, dark energy is a repulsive force that is causing the expansion of the universe to accelerate. It is as if the very fabric of space itself possesses a built-in anti-gravity, pushing galaxies apart at an ever-increasing rate. So the universe we call home is a profound mystery, a cosmic soup where the familiar world of atoms is just a minor flavor, overshadowed by the dominant, invisible influences of dark matter and the even more dominant, empty-seeming push of dark energy. We are living in a cosmos ruled by shadows. That flatness of the cosmos is not just a mathematical curiosity, it is a profound statement about the ultimate fate of our universe. The patterns imprinted on the ancient light, the specific sizes of those hot and cold spots, act as a cosmic ruler. Scientists use this ruler to measure the geometry of space itself. In a positively curved universe, shaped like a sphere, parallel beams of light would slowly converge. In a negatively curved universe, warped like a saddle, those light beams would steadily diverge. But the data from the cosmic microwave background shows something remarkably simple. Those beams of light have traveled for nearly 14 billion years in perfectly straight lines. This tells us that on the grandest possible scale, the universe is flat. The rules of geometry you learned in school, where the angles of a triangle always add up to 180 degrees, hold true across the entire observable cosmos. This flatness is a critical piece of the cosmic puzzle, deeply connected to the theory of inflation. That violent exponential stretching in the universe's first moments would have smoothed out any initial curvature, flattening the fabric of space in the same way blowing up a balloon to an immense size makes its surface appear locally flat. A flat universe also has a specific and dramatic implication for our future. It suggests that the density of matter and energy is precisely balanced at a critical value, meaning the expansion will continue to slow, but it will never quite stop and reverse into a big crunch. Instead, the cosmos will likely continue expanding forever, growing ever colder and darker, driven by the relentless push of dark energy. So the simple geometry of a flat plane, something we can draw on a piece of paper, writes the final chapter for our entire cosmos. Those subtle ripples in the cosmic background are more than just a temperature map. They are a fossilized recording of the universe's first sounds. To understand this, we must journey back to that primordial sea of particles and energy before light was set free. The early universe was not silent. It was a roaring, chaotic ocean, a seething plasma where protons and electrons were scattered in a thick fog, constantly battered by an intense storm of radiation. In this dense, hot medium, gravity was already at work trying to pull clumps of matter together, but it faced a powerful opponent, the tremendous pressure of the radiation itself, which pushed outward with immense force. This created a cosmic tug-of-war. Gravity would pull a pocket of matter inward, but as it compressed, the radiation pressure inside would build until it exploded back outward, like a spring. This cycle of collapse and rebound set the entire cosmos ringing. Spherical waves of compressed matter and energy began to race outward through the plasma, moving at over half the speed of light. These were not random noises, they were organized, predictable sound waves, and just like a musical instrument, the universe had a fundamental note, a tone dictated by its size and density. But then the music stopped when the universe cooled enough for atoms to form. Suddenly the fog cleared. The radiation, which had been locked in a tight dance with matter, was set free. The pressure that had been driving the sound waves vanished in an instant, and the waves froze in place, their final crests and troughs etched permanently into the fabric of space. We see this frozen music in the CMB as a subtle preference for certain sizes of hot and cold spots. These are the Barrian acoustic oscillations, the ghostly echoes of the first and only chord the universe ever played. What would it have been like to hear that single resonant note ringing from the beginning of time? That first chord of the universe was not a whisper, but a deafening roar of pure, brilliant light. The afterglow we detect today as a faint microwave signal was not always so cold and quiet. When this light was first set free, the universe was a searing inferno, thousands of times hotter than the surface of our sun. In that moment of liberation, the cosmic microwave background was not a microwave at all. It was a flash of blinding, white-hot light, blazing across the universe in visible and even ultraviolet wavelengths. If human eyes could have witnessed that event, they would have seen a cosmos filled with an unbearable, uniform glow, an orange-white radiance so intense it would have outshone anything we can possibly imagine. So how did that brilliant flash become the faint cosmic hiss we measure with our radio telescopes? The answer lies in the relentless expansion of space itself. As the universe has stretched over billions of years, it has also stretched the very light traveling through it. Think of a wave drawn on a rubber band. As you pull the ends of the band apart, the wave gets longer and its peaks become farther apart. This is exactly what happened to the universe's first light. Its wavelengths have been stretched by a factor of over 1,000 by the expanding cosmos. This process is what astronomers call redshift. The original high-energy, short-wavelength visible light has been shifted all the way down the electromagnetic spectrum into the long, low-energy domain of microwaves. That is why we need specialized instruments to detect it. We are essentially listening to a song that has been dramatically slowed down, its pitch lowered from a cosmic scream to a faint background hum. The light itself has not changed, but the fabric of reality has stretched around it, transforming its very nature and preserving it as a cooled fossil of a far more violent time. This moment of liberation, when light broke free, is known to cosmologists as recombination. It is a slightly misleading name, for the particles were not combining again, but for the very first time. The universe was a searing plasma, a chaotic soup of bare atomic nuclei, which are positively charged protons and free, negatively charged electrons. In this superheated state, these charged particles were like tiny mirrors, constantly scattering and trapping the intense light, preventing it from traveling any meaningful distance. A photon could not go anywhere without immediately bouncing off an electron, but the universe was expanding and cooling relentlessly. After about 380,000 years, it finally dropped below a critical temperature of around 3,000 degrees Celsius. This was cool enough for the electrical attraction between the positive protons and negative electrons to finally overcome the chaotic thermal energy. They snapped together, forming the first stable neutral atoms, almost all of them hydrogen. In an instant, the fog cleared, the free electrons were gone, captured into atoms. The road was suddenly open. The photons that had been bouncing around helplessly were now set free, released to travel across the cosmos in a great flash. This is the flash we detect today as the cosmic microwave background. That first brilliant gleam of free light is a direct snapshot of the universe at the precise moment the last electron was captured by the last proton, the instant the cosmic fog lifted forever. What we are seeing is the afterimage of the universe becoming transparent, the final glow from the formation of the very first atoms. But for all its detailed perfection, the Planck map holds a few stubborn blemishes, and one of them is truly colossal. Stretching across a vast swath of the southern sky is a mysterious region so profoundly cold it defies easy explanation, a feature astronomers call the CMB cold spot. This is not a tiny fluctuation, but a gigantic chill, an area of space where the ancient background light is significantly cooler than the average. If the CMB is a near-perfect tapestry of the infant universe, the cold spot is a prominent, unexplained thread woven into its fabric. One leading theory suggests it might be the ghostly imprint of an immense cosmic void, a truly empty region of space spanning perhaps 1 billion light years. In such a vast emptiness, there will be far fewer galaxies and less matter than expected. As the universe's first light traveled through this void on its long journey to us, it would have lost a tiny amount of energy, a process driven by the expansion of space itself, making it appear colder to our telescopes. It would be the largest structure of nothingness ever discovered, yet when astronomers survey that region of the sky, they have not found a void large enough to fully account for the profound cold. This discrepancy has fueled more exotic and thrilling possibilities. Some theorists propose that the cold spot could be evidence of a cosmic bruise, a remnant of a collision between our universe and a bubble of another universe in the vast multiverse. According to this mind-bending idea, the energy released in such a primordial collision could have left a permanent, cooler scar on our cosmic background. While this remains a highly speculative hypothesis, its very consideration highlights how deeply puzzling this feature truly is. The cold spot remains one of the most active and tantalizing puzzles in modern cosmology, a cosmic anomaly that whispers of either a staggering emptiness or a window into realities beyond our own. Even the universe's baby picture seems to have a preferred direction, a strange alignment that challenges our most fundamental assumptions. Scientists have discovered that some of the largest features in the cosmic microwave background, the very ripples that seeded galaxies, are not randomly distributed as our models insist they should be. Instead, they appear to be subtly aligned along a particular axis, a cosmic preferred direction that some have whimsically and dramatically nicknamed the axis of evil. The name itself reflects how unsettling this finding is to the core principle of cosmology, the Copernican principle, which states that the universe has no special place or direction. We should not be able to look at a map of the entire cosmos and point to an axis that seems more significant than any other. It would be like looking at a vast, featureless ocean and realizing all the waves are mysteriously lined up in one specific direction. So what could this mean? The most conservative explanation is that it is simply a statistical fluke, a trick of the data that will vanish with more precise observations. Yet it has stubbornly persisted through data from WMAP and Planck. Another possibility is that there is a subtle, unaccounted for bias in our measurements, perhaps an effect from our own solar system's motion through the cosmos that we have not perfectly subtracted. But the most profound and thrilling possibility is that the axis of evil is a real cosmic feature, a fossilized imprint from a time before the Big Bang. Some theories suggest our universe was not born in perfect isolation, but that its birth was influenced by a pre-existing structure or a collision with another realm, an event that left a directional scar on the very fabric of our reality. This anomaly whispers that the cosmos might not be perfectly uniform after all, and that its origin story may be even more complex and wondrous than we ever dreamed. The temperature map of the ancient light is only half the story. To read the full cosmic chronicle, we must also observe its polarization, the specific direction in which those primordial light waves are vibrating. Imagine the surface of a calm pond. When you drop a single pebble, it creates circular ripples that vibrate in all directions. But if you drag a stick through the water, you create waves that are polarized, vibrating in a single, organized plane. The light of the cosmic microwave background carries both kinds of imprints from its turbulent birth, the violent push and pull of matter and radiation in the early universe. Those very first sound waves created one type of polarization pattern known as E-modes. These are relatively straightforward, like the ripples from the stick, and they give us a sharper view of the density and distribution of matter in the infant cosmos. But there is another, far more elusive signal buried within this polarized light, a pattern known as B-modes. These are a curl, a swirly pattern imprinted not by the clumping of matter, but by something far more profound, the fabric of space-time itself being stretched and squeezed. This is the potential signature of primordial gravitational waves, ripples in the very geometry of the universe generated in the first split second of inflation. Detecting these B-modes would be like finding the direct fingerprint of the universe's violent, exponential growth spurt, a whisper from a time when the entire cosmos was smaller than a single atom. It is the next great frontier in our quest to understand creation, a signal so faint it has so far eluded our most powerful detectors. What other secrets are encoded in the subtle, swirling dance of the universe's first light? The hunt for these elusive B-mode signals has become one of the most dramatic and challenging quests in modern science. Teams of astronomers have set up powerful telescopes in some of the most extreme environments on Earth, high on the cold, dry plateaus of the South Pole and the high deserts of Chile, where the thin, clear air offers a pristine view of the cosmos. One of the most famous of these projects is known as BICEP, the background imaging of cosmic extragalactic polarization. For years, the BICEP team scanned a small, clean patch of sky, and in 2014, they announced a historic breakthrough. They believed they had finally detected the faint, swirling pattern of primordial B modes, the direct signature of gravitational waves from the universe's violent inflationary birth. The announcement sent shockwaves through the scientific community and the world, hailed as evidence for the very first moments of creation, but then came the sobering reality. The cosmic signal they detected was incredibly faint, and it was competing with a much closer source of interference, interstellar dust right here in our own Milky Way galaxy. This dust, made of tiny, magnetically aligned particles, also emits polarized light that can mimic the exact swirling pattern of the primordial B modes. Further analysis with data from the Planck satellite revealed the difficult truth: a significant portion, if not all, of the thrilling signal was contaminated by this cosmic dust. It was a powerful lesson in humility, demonstrating the immense difficulty of separating the faintest echo of creation from the foreground noise of our own galactic neighborhood. This setback did not end the search, it refined it. Scientists now use ever more sophisticated instruments and detailed maps of galactic dust to subtract its confounding signal, peeling back the layers of the cosmos in the hope that one day the pristine whisper of inflation will finally be heard. These frozen sound waves give us more than just a history. They provide a precise cosmic ruler. The Baryon acoustic oscillations imprinted in the cosmic microwave background have a known physical scale. We understand the physics of that primordial plasma so well that we can calculate the theoretical size of these ripples at the moment the universe became transparent. This means the distance between the hot and cold spots in that ancient light is a standard ruler of a known length, etched into the sky. The real power comes from comparing this known size to the apparent size we measure from Earth. Imagine you know the exact height of a friend standing far away across a vast field. By measuring how small they appear to your eye, you can calculate the distance to them across that field. Cosmologists do the same thing with the universe. They know the true size of these ancient ripples, and by meticulously measuring how large they appear to us as an angle on the sky, they can triangulate the distance back to the surface where the CMB originated. This single measurement unlocks profound truths. The apparent size of these standard rulers is exquisitely sensitive to the geometry and contents of the universe. A universe filled with more dark energy, for instance, would have stretched more over time, changing the apparent angular size of these ripples in a specific way. By applying this cosmic ruler, scientists have been able to pin down the Hubble constant, the number that describes how fast the universe is expanding today. It is a fundamental pillar of modern cosmology, all measured from the subtle spacing of patterns in the oldest light we can see. This ancient whisper does not just tell us where we came from, it measures where we are going. The universe's oldest light is the ultimate arbiter of truth. Every grand theory of cosmic origins, every alternative to the standard Big Bang, must eventually stand before the evidence etched into the cosmic microwave background. This primordial glow is not just a historical record, it is a judge delivering a verdict on the validity of our boldest ideas. For decades, competing models have tried to explain our cosmos. The once popular steady-state theory, for instance, proposed that the universe had no beginning and has always looked the same, with new matter continuously created to fill the gaps as it expands. Yet this elegant idea makes a very specific prediction: that the universe should be uniform not just in space but in time. It should not have a hot, dense past. The discovery of the CMB, a clear and pervasive relic of a searingly hot beginning, was a blow from which the steady-state theory could not recover. The ancient light testified to a definite birth, a moment of creation that the theory simply could not accommodate. Other models, like various cyclic universe scenarios that propose an endless series of big bangs and big crunches, also face a stern test. They must account for the specific pattern of hot and cold spots, the precise blackbody spectrum, and the stunning uniformity of the background radiation. So far, none have been able to reproduce the exquisite details captured by COBE, WMAP, and Planck without incorporating some version of a rapid inflationary period at the dawn of time. The data is so precise, so unforgiving, that it has effectively cornered the marketplace of viable cosmic models. Any new theory must not only be mathematically beautiful, it must also reproduce the specific, modeled whisper we have mapped across the sky. The CMB has raised the bar for cosmic storytelling, demanding that any narrative of our origins must align perfectly with this fossilized echo from the dawn of time. The universe was born in a single decisive moment of transformation. We often speak of the Big Bang as a fiery explosion, but the most critical event was a burst of expansion so rapid it defies all intuition. This was cosmic inflation, a period when the fabric of space itself stretched faster than the speed of light, all within the first fleeting fraction of a second. The cosmic microwave background, born 380,000 years later, is our most direct evidence for this ancient growth spurt. Its profound smoothness, that near-perfect uniformity across the sky, is the first great clue. Only a process that stretched a once tiny, interconnected region into our vast cosmos could have ironed out the wrinkles so completely, but inflation did more than just smooth the cosmos, it also made it noisy. The same quantum processes that operate on the tiniest scales were amplified by this violent expansion, stretched from the subatomic world to cosmic proportions. These quantum jitters became the seeds for the density variations, the tiny ripples in temperature we see etched into the ancient light. Without that initial unimaginable stretch, the universe would have remained a bland, featureless sea, with no gravitational seeds to ever form a single star or galaxy. So when we look at the modeled pattern of the CMB, we are not just seeing a baby picture from 380,000 years old. We are glimpsing the magnified imprint of quantum fluctuations from the first trillionth of a second, frozen into the sky by the incredible power of inflation. This profound uniformity presents one of cosmology's greatest puzzles, the horizon problem. How could the entire sky from one edge to the other display such a perfectly even temperature? The laws of physics dictate that for two regions to reach the same temperature, they must have been in thermal contact, able to exchange energy and balance each other out. Yet when we trace the paths of light from opposite sides of the cosmic microwave background, we find a startling contradiction. These regions are so far apart that even light, traveling at the universe's ultimate speed limit since the moment of recombination, would not have had enough time to cross the vast distance between them. They were forever beyond each other's horizons, isolated islands in the newborn cosmos with no possible way to communicate. It is as if you walked into a vast, crowded ballroom and found thousands of complete strangers who had never met or spoken, all holding cups of coffee at the exact same temperature to the millionth of a degree. This cosmic synchronization seems utterly impossible within the standard Big Bang model. The universe that appeared had to have been born much, much smaller. This is where the theory of cosmic inflation provides an elegant and breathtaking solution. It proposes that in the first fleeting fraction of a second, a subatomic speck of space underwent a violent, exponential expansion, stretching faster than the speed of light. In that unimaginably brief instant, a single, tiny, and thoroughly interconnected patch was magnified to a size larger than our entire observable universe today. Every part of our cosmic horizon was once crammed into that infinitesimal dot, in intimate contact with every other part. This primordial unity allowed the temperature to perfectly even out before the great stretching began. Inflation took that initial equilibrium and blew it up to a cosmic scale, imprinting the smoothness we now observe across the sky. The horizon problem vanishes when we realize that the farthest reaches of space were once our closest neighbors, all sharing the same cosmic conditions before being flung apart by the universe's most dramatic growth spurt. This ancient glow is not a static monument, but a fading ember. The temperature of the cosmic microwave background is imperceptibly, yet inexorably, dropping. This is a direct consequence of the universe's relentless expansion. Every moment as the fabric of space itself stretches, it pulls on the ancient light traveling through it, lengthening its wavelengths even further. Think of drawing a wave on a stretchy rubber band, then slowly pulling the ends apart. The wave crests move farther from each other, and the entire wave becomes longer and flatter. This is precisely what is happening to the photons of the CMB on their multi-billion-year journey. As the wavelength of light increases, its energy decreases, and we perceive that as a drop in temperature. The change is incredibly slow, a cooling of less than 1/1,000,000th of a degree over a million years. Yet across cosmic timescales, This fate is definitive. When the CMB was first set free, it blazed at nearly 3,000 degrees. By the time our solar system formed, it had already cooled to a few degrees above absolute zero. Today it registers at 2.725 degrees, and in the far future it will approach the ultimate chill of absolute zero. The universe's first light is not just a relic, it is a dying echo, its warmth slowly being stolen by the expanding void. What does it mean that the earliest song of creation is gradually falling silent? This ancient light serves as a cosmic backlight, illuminating everything in its path. As the faint whisper of the CMB travels for billions of years to reach us, it does not always journey through empty space. It must pass through the vast, modern structures that grew from its own primordial seeds, like giant galaxy clusters. These clusters are the largest gravitationally bound objects in the universe, and they are filled with incredibly hot gas, so hot that it glows in X-rays. When photons from the cosmic microwave background plunge through this searing intergalactic plasma, a subtle but crucial interaction occurs. The hot, energetic electrons in the gas collide with the much colder, ancient CMB photons. In these collisions, the electrons transfer a tiny amount of energy to the photons, giving them a slight boost. This process is known as the Sunyaev-Zeldovich effect. Think of it as a cosmic game of pinball. The CMB photons are like slow-moving balls, and the super-fast electrons in the cluster gas are the flippers. Each time a photon hits an electron, it gets kicked to a slightly higher energy level. This creates a distinct telltale shadow in the CMB map. At the location of a massive galaxy cluster, the microwave background appears slightly dimmer and distorted in a specific way. It is not a shadow of darkness, but a shadow of altered energy, a cold spot that is actually a sign of the photons being heated up and pushed to a different part of the spectrum. For astronomers, this effect is a powerful tool. It allows them to use the entire sky as a backdrop to find these colossal clusters, regardless of how far away they are. By scanning CMB maps for these characteristic distortions, they can detect the silhouettes of galaxy clusters that are otherwise too distant or faint to see easily with optical telescopes. The universe's oldest light is not just a fossil to be studied, it is an active probe, a flashlight we can use to illuminate the hidden architecture of the cosmos. What other invisible structures might be revealed in the shadow play of this primordial glow? That means the oldest thing any human eye can perceive in any form is this cosmic fossil. When you look at the stars in the night sky, you are seeing light that is thousands or even millions of years old. But when you detect the cosmic microwave background, you are witnessing light that has been traveling for almost the entire history of existence, a staggering 13.8 billion years. To put that immense age into a human perspective, if the entire lifespan of the universe were compressed into a single calendar year, with the Big Bang at the stroke of midnight on January 1st, the light of the CMB was released in the very early morning of January 1st. All of human history from the first cities to the present day would occupy less than the final second of December 31st. This is the ultimate time capsule. And remarkably, you have likely encountered this ancient echo without even realizing it. Before the era of digital broadcasts, an old analog television set tuned to a dead channel would display a flickering screen of black and white static. That familiar snowy pattern was mostly random noise from various electronic and atmospheric sources, but buried within that chaos, a tiny fraction, about 1% of that flickering signal, was something far more profound. It was the actual physical afterglow of the Big Bang, the universe's oldest light, being picked up by your television antenna. The cosmic birth of everything was quietly playing out in the background of your living room, a ghostly whisper from the dawn of time manifesting as a mundane, everyday sight. It is a humbling thought that the most ancient story ever told was once accessible by simply turning a dial. Yet for all its perfection, this cosmic fossil is not entirely flawless. The spectrum of the cosmic microwave background is the most perfect blackbody ever measured in nature, a curve of radiant energy so ideal it precisely matches the predictions for a cooling ember from the Big Bang. But if you listen with exquisitely sensitive ears, you begin to hear the faintest of imperfections, tiny distortions in this otherwise perfect hum. These are not the temperature ripples that seeded galaxies, but subtle shifts in the very color and energy distribution of the light itself. They are like tiny scratches on a pristine, ancient recording, hints that the early universe was not a perfectly isolated chamber. The primary source of this perfection is the era of recombination itself. When the universe became transparent, the intense, frequent collisions between particles and light had effectively thermalized the radiation, forcing it into that perfect blackbody curve. Any process that injects a significant amount of energy into the cosmos after this moment, but before the universe was fully settled, could have left a permanent scar by distorting that perfect spectrum. Imagine the CMB as a perfectly still pond. If you were to gently heat a small section of the water after it had calmed, you would create a subtle, lingering patch of warmer water that disturbs the perfect stillness. In the cosmic context, one potential source of such heating could be the decay of exotic theoretical particles from the early universe. As these mysterious particles faded from existence, they would have dumped energy back into the primordial gas, subtly reheating it and leaving a unique fingerprint in the background light. Another potential culprit is the fierce radiation from the very first generations of stars. These primordial giants, burning ferociously and dying young, could have flooded the early cosmos with ultraviolet light, enough to subtly reionize pockets of gas and impart a tiny distortion on the CMB's perfect spectrum. Detecting these spectral distortions is the next great observational frontier. Future space missions designed with phenomenal sensitivity are being planned with the explicit goal of measuring these minute deviations. Finding them would be like discovering a hidden diary entry from the universe's dark ages, a period after the CMB was released, but before the first galaxies fully formed. It would open a direct window into energetic events that have so far been completely invisible to us, revealing the whispers of dying particles or the first dawn of starlight in a cosmos emerging from darkness. The implications of inflation stretch far beyond our own cosmic horizon into a realm of pure speculation. The same physics that so elegantly explains the smoothness and structure of our universe also hints at a reality of almost unimaginable scale. If the fabric of space-time experienced one episode of exponential, faster-than-light stretching, what is to say it stopped? Many theoretical models suggest that inflation is not a one-time event, but an eternal process, a runaway engine of creation. In this view, our entire observable universe, everything we can see in the CMB and beyond, is just one bubble in a vast, frothing cosmic foam. Each of these bubbles is a separate universe, inflating into its own domain, potentially with its own unique set of physical laws and constants. The force that drives inflation, a field known as the inflaton, might not settle into a single stable state everywhere. Instead, it could decay randomly in different patches of the primordial chaos, each decay event triggering a new Big Bang and spawning a new bubble universe. In some of these bubbles, the strength of gravity might be stronger or the nuclear forces weaker. Some might be rich with complex chemistry, while others might be stillborn, collapsing instantly or expanding into barren emptiness. Our universe, with its specific life-permitting rules, would then be just one fortunate outcome in an infinite cosmic lottery. The detailed patterns in the cosmic microwave background, the very ripples we use to confirm inflation, are the only clues we have to the conditions that might have started this eternal process. While the multiverse remains a highly speculative and profoundly untestable idea, it emerges naturally from the mathematics that so perfectly describes our own origins. It suggests that our entire cosmic history, from the first flash of light to the rise of galaxies, might be just a single chapter in a story without end. This ancient light provides a fixed backdrop for the entire cosmos, a universal reference frame against which all motion can be measured. We are not sitting still in the universe, and the cosmic microwave background proves it. As our solar system journeys through the galaxy and our galaxy speeds through the cosmos, we are moving relative to this primordial glow. This motion leaves a distinct fingerprint on the CMB, an effect known as the dipole anisotropy. Imagine you are standing still in a gentle uniform rain, feeling the droplets fall evenly on your head and shoulders. Now begin to run forward. Suddenly, you feel more raindrops hitting your front while your back feels relatively dry. You are not actually creating more rain in front of you, but your motion through the stationary shower makes it appear that way. This is precisely what happens with the ancient light. Because we are moving at tremendous speed through the sea of CMB radiation, the light directly ahead of us appears compressed or blue-shifted, making it seem slightly hotter. Conversely, the light coming from behind us is stretched or redshifted, making it appear colder. This creates a hot spot in the sky in the direction of our motion, and a corresponding cold spot directly opposite. By meticulously mapping this temperature difference, scientists have calculated our velocity. Our entire local group of galaxies is racing through the universe at approximately 370 kilometers per second relative to this primordial rest frame. We are cosmic travelers, and the faintest whisper of the Big Bang is the wind on our face, revealing both our speed and our direction through the vastness of space. That primordial glow was the universe's first dawn, but it was followed by a profound and lengthy cosmic night. After the release of the cosmic microwave background, the universe plunged into what astronomers call the Dark Ages. For millions of years, the cosmos was a vast expanding sea of neutral hydrogen and helium gas, shrouded in utter blackness. No stars had ignited yet, no galaxies had begun to swirl. The only light was the fading afterglow of the Big Bang itself, stretching further into the microwave spectrum and cooling with every passing eon. It was a silent, featureless expanse, waiting in the dark for gravity to do its slow, patient work. This era of darkness finally ended when the first generation of stars, known as population 3 stars, burst into life. These were not like the stars we see today. They were behemoths hundreds of times more massive than our sun, and they burned with a ferocious, short-lived intensity. Their brilliant ultraviolet radiation acted like a cosmic firestorm, flooding the universe and violently stripping electrons from the neutral hydrogen atoms that filled the void. This monumental process, called reionization, tore apart the very fog that had once trapped light, transforming the cosmos from a neutral state back into a plasma of charged particles. But this time, the universe did not become opaque because the gas was now too diffused to fully trap the light. The epoch of reionization, sparked by the first starlight, permanently cleared the cosmic fog, making the universe transparent to the high-energy light of stars and galaxies for all time. The story of this transformation is not lost to history. It is subtly encoded in the polarization of the cosmic microwave background. As the fierce light from those first stars and galaxies encountered the CMB, it scattered off the newly freed electrons, imprinting a specific, large-scale pattern on the light's polarization. By carefully analyzing these faint swirls in the ancient glow, cosmologists can trace the timeline of reionization, understanding when the first luminous objects emerged to end the long, dark silence and illuminate the cosmos for good. The hunt for the universe's first whisper is far from over. A new generation of cosmic eavesdroppers is preparing to listen with a sensitivity that will make our current maps seem like faint sketches. On the high, dry plateaus of the Atacama Desert in Chile and from the pristine cold of the South Pole, colossal new observatories are taking shape. Projects like the Simons Observatory and the even more ambitious SIMBS-4 represent a quantum leap in our ability to see the ancient light. There are not single telescopes, but vast arrays of detectors, thousands upon thousands of superconducting eyes, all working in concert to scan the microwave sky. Their primary mission is to achieve what has so far been impossible, to capture the pristine signal of primordial B modes, the swirling fingerprint of gravitational waves from the universe's inflationary birth. To do this, they must peer through the veil of galactic dust with unprecedented clarity, separating the cosmic signal from the local noise with a precision we can only now dream of. But their ambition does not stop there. These powerful instruments will map the polarization of the cosmic microwave background in such exquisite detail that they could uncover subtle signs of new physics, perhaps even evidence for exotic particles that have so far eluded our largest particle colliders. They will act as time machines, looking past the dawn of the first stars to study the dark ages in incredible detail, and they will use the SIMB as a backlight to census virtually every massive galaxy cluster in the observable universe. Beyond these ground-based behemoths, plans are already being drawn for a future space mission, a successor to Planck that would operate in the perfect silence of space, free from the interference of Earth's atmosphere. This next-generation satellite would deliver an all-sky map of the CMB's polarization with such fidelity that it would either finally confirm the inflationary paradigm or, far more thrillingly, reveal something entirely unexpected that forces us to rewrite our cosmic story. The faint afterglow of the Big Bang has not yet yielded all its secrets, and the next decade promises to listen more deeply than ever before. This faint echo of heat connects our tiny world to the grandest story ever told. Decoding the universe's oldest light stands as one of humanity's most profound achievements. From our small planet, we have learned to listen to a whisper from the beginning of time, a signal so subtle it was once mistaken for pigeon interference. Through patience and ingenuity, we have translated that whisper into a complete cosmic biography. We have measured the age of everything, traced the blueprint for every galaxy, and uncovered a universe composed mostly of mysterious, invisible forces. We have read our ultimate fate in the geometry of space and heard the frozen echoes of the first sound. This knowledge transforms our place in the cosmos. We are not merely passive inhabitants of a vast, indifferent universe. We are the universe itself, become conscious, looking back at its own origins. The atoms that form our bodies were forged in the hearts of long-dead stars, but the pattern for those stars was imprinted in the cosmic microwave background. We are the descendants of those primordial ripples, the universe's way of understanding its own breathtaking history. This cosmic heritage binds us to everything we see and everything we have yet to discover. The story continues, and we are both its readers and its characters. From a faint hiss mistaken for pigeon interference to a cornerstone of modern cosmology, this ancient light has guided us through the universe's deepest secrets. We have traced its journey from a theoretical prediction to an accidental discovery that confirmed our cosmic origin story. We have seen how its perfect smoothness demanded a theory of breathtaking inflation, and how its faintest ripples grew into the galaxies we see today. This primordial glow has given us a precise cosmic recipe, revealing a universe dominated by mysterious dark matter and dark energy, and it has even hinted at the possibility of a vast multiverse. Each fact we have explored, from the frozen sound waves of creation to the profound cold spot and the unsettling axis of evil, is a testament to our relentless curiosity. The cosmic microwave background is more than just a fossil. It is our most direct and profound link to the origin of everything. It connects our tiny present moment to the very first flash of light, telling the story of where we came from and where we are going. So as we conclude this journey through the universe's oldest light, we want to hear from you. Which of these 30 facts astonished you the most? Was it the accidental discovery, the idea of frozen sound waves, or the mind-bending concept of inflation? Share your thoughts in the comments below, and if you are hungry for more explorations into the cosmos, be sure to subscribe for more deep dives into the mysteries of the universe.